All right. So for number one, we got to describe what's going on in each lettered interval. So what's happening in section A? It's stopped, not moving. Okay, anything that would imply the object is essentially doing nothing at that point. Okay, what's going on in part B? Moving forward at a constant velocity. Just if you say forward, you can't say speed. Speed's scalar. Okay. If you're saying moving forward, I'll accept it today, but in the future, guys, you got to say if you give a direction, it's got to go with a vector quantity. You can't give a scalar quantity with a direction. Okay. Okay, I'll accept that today, but again, in the future, I'm going to want specificity on velocity. Yeah, I mean, there's no direction really given here, so it could be up. Yeah. Okay. No, because it doesn't imply that that movement was constant. It could have moved 40 meters in 2 seconds while accelerating. Yeah. Not specific enough. No, it had. If it said forward, I'd accept it, but it didn't say forward or up or in a positive direction. Okay, for part C, again, not moving, stopped, doing nothing. Okay, something like that. And in part D, moving backwards at a constant velocity, and the same rules apply as did for B. I'll accept at a constant speed as long as it said backwards or in a negative direction. Okay, something like that. But if it only said, constant speed, then it's not. It's got to have that direction on it. Okay, so 1 mark each for those. Okay, so 1 mark each for those descriptions. And then calculating the velocity in section D. Okay, velocity is displacement over time. The displacement in part D is 40 meters backwards, or negative 40 meters. Okay, and the time is 1.5 seconds, because it starts right here. Okay, so if they have something like this, give them a mark. Okay, and then our final answer here should be, oh, I don't have it on there. Okay. Okay, so we got negative 40, okay, divided by 1.5. All right, so we got 26.7, we'll say 26.7 meters per second, and it's either negative or it's backwards, or down, I guess we could also say, okay, because it is a vector quantity and it does need to have a direction on it. Okay, so negative 26.7 meters per second. They also have to have units. If there are no units on that answer, it's wrong. Okay, they have to have units and they have to have direction on there. All right, so that's the 6th mark on that one. Questions there? Okay. Question number 2. We want to calculate the average speed. What 2 things do I need? Yeah, total distance and total time. All right, so that's what I need. I've got to get that off of the graph. So here's where the marks start. Okay, they're going to get a mark for each proper distance on this graph. Okay, so in this first part here, they went 20 meters. I don't care how they showed the work for that or whatever, as long as they got that it went 20 meters in that first part. Okay, I said, guys, at the start of the quiz, show all your work. There's a bunch of intermediate steps. These are the intermediate steps. Okay, didn't do anything in that part, then went from 20 to 40, which is another 20 meters, and then another 20 meters. Okay. Then they're not going to get marks for these. Okay. All right, so our total distance here, so 1 mark here, 1 mark here, 1 mark, 1 mark, okay? They've got their total, and guys, if they didn't write the 0, I mean, they just may have just gone, well, it's not, there's nothing. I'll accept that. I probably wouldn't have written that myself, okay? So we'll have 60 meters over 12 seconds, okay? And that should give us 5 meters per second. All right, so that will be 4 marks, 5th mark, 6th mark. Okay, Quiz is out of 12, so give them a mark out of 12 at the top, and then I would like them handed to me at the front here, please. Just a little, yeah. Okay, so velocity versus time graph. So reminders of things we can read off of velocity versus time graph. We can read how fast the object is going at any point in time. Don't have to do any calculating, that's read directly off the graph. I can calculate the acceleration of the object by either finding the slope of a line in a certain section or by using the acceleration formula. A equals VF minus VI over T. Okay, and that's going to be one of the things you're going to have to do. Okay, and I can calculate the displacement of the object. To calculate displacement, I need average velocity times time. Okay, that's easy for a section of the graph that looks like this part does, because it's not changing its velocity, and the average velocity is the same the entire trip, 2 meters per second for that part. Okay, but in other parts of the graph, the velocity is changing. Okay, there's still an average velocity during those parts. Okay, and if you recall, I was telling you about how you can calculate the displacement by finding the area between the line and the x-axis. Okay, we call that under the line, but when you're in the negative, it kind of looks like it's over the line. Okay, so we've got here, basically got to draw a whole bunch of shapes. Okay, so I got a bunch of shapes now that I can calculate, because now I've isolated different actions during the trip. Some of them are accelerating, some of them are moving forward, some of them are moving backward, okay, all of that kind of stuff. So I've isolated in each one of those kind of sections of the graph. So for this first line right here, okay, actually it's the second line. What's going on right here? Nothing, okay? The velocity is 0 for 2 seconds. So nothing, he doesn't have any displacement there. Okay, but here he accelerates from 0 to -3 meters per second, and he does that in 3 seconds. All right, so he's got an average velocity between 0 and 3 that would be 1.5. His average velocity during this time would be -1.5 meters per second, because it's halfway between 0 and -3. Okay, everybody follow me there. Okay, if you're changing your velocity uniformly, okay, if I go from 0 to 10 meters per second and I do that at a uniform rate, my average velocity is 5. Because for half of the trip, I was going slower than 5. For half the trip, I was going faster than 5. Exactly half. That makes 5 the midpoint, the average of that acceleration. Okay, everybody okay with that? All right. Okay, so the reason that this works then, finding average velocity times time being the area under the line, is because the height of the triangle is always, okay, or half of the height of the triangle is always that halfway point, that middle velocity for that section, okay, because it's showing a velocity versus time graph. So average velocity here times time is really like saying the base of the triangle, which is time, times the height of the triangle over 2, which is the average velocity. Okay, half of whatever their maximum velocity was that they reached. Okay. All right, so for each section of this graph, I've got to calculate the area of all of those shapes and then do what with them? Add them together. Okay, because I've got to get the total distance traveled to get the total or the average speed. Okay, to get the total displacement, okay, sorry, I confused myself there. I used the wrong term. Okay, to get the total displacement, I got to find all these areas and add them up. What if the area is negative? Then I put a negative in there. Okay, that's fine. We're going to add them up with the negatives and positives part of it. Right? Calculate all of the areas on there, add them up, the positives and negatives included, and you'll find out the guy's total displacement. Essentially, you got to make shapes out of anywhere where the line changes direction. Okay, so here and here have different slopes. I can't just use this one triangle. Okay, so I'm going to use this triangle here, and it gets a little hairy because this one here is only half a second. Okay, like the base of it's only half a second, and then here the base would be 1.5 seconds for this big triangle. Okay, so this one here, the height of this triangle is -3. The base of this triangle is 3. Okay, so 3 times -3 is -9, divided by 2 is -4.5. All right, so we'll have, right, the displacement in this triangle here is 4.5, -4.5. All right, then I've got this triangle here. So it's going to be -3 times 1 over 2. So he goes 1.5 in this part, -1.5. Follow me there? Okay, for this triangle, the height of the triangle is 3, okay, over 2 times 1. Okay, this is the base of the triangle. This is the height of the triangle over 2. Okay, so 3 over 2 is 1.5 times 1 is 1.5, -1.5. Why is it negative? Because the height of the triangle is -3. Okay, I know what you're thinking. The line is going back up here, right? Okay, that's fine. The line's going up, but his velocity is still negative. Okay, as long as the line is below 0, his velocity is negative. He's accelerating that way, but he's still moving that way. Okay, all right, watch this. As soon as it leaves my hand, it's accelerating down, still moving up. That's why it slows down. Okay, I can accelerate forward and move backward. I'm just not going to keep moving backward. I'm eventually going to start moving forwards because my acceleration is forwards. Right, or a bungee cord. Okay, like when you bungee jump, like you're falling, you're accelerating downward, but as soon as the bungee cord starts to take up, your acceleration is up. That's why you don't hopefully crash into the bottom. Okay, because the cord is going to accelerate you up and cause you to stop and then start moving back up again. Okay, because you do kind of do that bouncy oscillation thing for a little while. Okay, with a bungee cord, or if someone put like a bungee cord across like a hallway and you ran towards it. Okay, as soon as you hit the bungee cord, okay, you are accelerating backwards because the bungee cord's pushing you that way. You might still be moving forwards, but you're not going to keep moving forwards. You're going to eventually get shot backwards. Okay, does that make a little more sense? Yeah, mind-blowing stuff. Yeah. All right, so let's just walk through. Let's walk through the rest of this one. Okay, so we've got this area here. So we've done this one now. So we got 4.5 plus 1.5. Then we've got this little triangle here. It's got a base of 1 and a height of 2. Okay, so that means its area is going to be 1. 2 times 1 over 2 is 1, but it's positive now. Okay, because it's above the line. Then we've got this rectangle, which is 1, 2, 3, 4, 5 along the base and 2 high. So 2 times 5. That one will be positive 10. Okay, then we've got this skinny little triangle. 2 times 0.5 is 1, divided by 2 is 0.5. Okay, then we've got this tall negative triangle that has a height of -6 and is 1.5 long. So 6 times 1.5 is 9, divided by 2 is -4.5. Running out of room here. Okay, and then I've got this triangle here. Okay, so for this triangle, I'm going to have a height of, because it only goes to here now, right? So its height is 4. Okay, its height is 4 and its width is 2. Okay, so 4 times 2 is 8, over 2 is -4. Okay, and then I've got this rectangle, which is 1, 2, 3, 4 wide by -2 tall. So that's going to be -8. Because it's a rectangle, I don't have to divide it by 2. And then I've got this triangle right here that is -2 high and 1 long. Okay, so -2 times 1 is -2, divided by 2 is -1. All right, so I've got all of those that now I have to add together to get the total displacement. Figure out this one here. So I found this triangle, the rectangle, and the triangle. Right, because it's just base times height to find the area of a rectangle. Right, 5 times 2, right. Okay, so we'll have our -4.5 plus -1.5 plus 1 plus 10 plus 0.5 plus negative 4.5 plus negative 4 plus negative 8. And of course, you could just subtract if you wanted to, but I'm a physics guy and it's a vector addition to me. Okay, plus negative 1. Okay, negative 12. I think that's what I had for the answer, right? Okay, so negative 12 meters is our total displacement. And if we look at the graph, that kind of makes sense. The graph is below the x-axis more often than it's above. Okay, this thing was moving backwards way more than it was moving forwards. Okay. All right, did anyone have any trouble with part A, finding the acceleration there? Okay, and I was just using that formula there, right? And we'll talk more about that probably tomorrow. We'll start acceleration. Okay, keep going there. For part C, okay, average velocity over the whole trip. Remember, guys, this is a different kind of graph. This is a velocity versus time graph. Okay, a lot of people are looking at it and going, all right, so the initial velocity was 0, the final velocity was 0. That must mean the average was 0. Well, no, it was clearly going backwards more than it was going forwards. They don't cancel each other out that way. Okay, what's the best way to calculate average velocity, even without a graph? The total displacement divided by the total time. We just calculated, spent all that time finding all those areas and calculated the total displacement to be negative 12. The total time is 20 seconds. Negative 12 over 20 is negative 0.6 meters per second. Okay, there's our average velocity. All right, you don't necessarily always have to use lines on the graph. If you've used lines on the graph to find something, you can use it after. Okay. Formulas are just as good as graphs most of the time. I know, guys, it's confusing. It will be for a little while, but the more we do it, the better at it we're going to get. I think we'll spend some more time on this tomorrow before I go into acceleration. Right. Right. So for total distance traveled, guys, so question came up here. How do I calculate the total distance traveled for this? I take all these displacements that I found before, and I make them all what? Positive, and add them up. Okay, same as I would have on a position time graph. I make them all positive, add them up. Yep. It should end at 15. Yeah, so you're looking at this and this. Yeah, they're identical. Top and bottom are identical. Just inverse of each other, right? Okay, so guys, everyone just hold up here for a sec. Looking up here. Okay, on a graph like this, sometimes you can just look at a graph and know the answer. This is a graph that's a prime example of that. Total displacement over the whole trip. Okay, it's a velocity versus time graph, and the part that's above the x-axis and the part that are below the x-axis are identical. So they spend as much time below the x-axis as they do above, which means these two things do what to each other? They cancel each other out. What's their total displacement? 0. Okay, without having to do any math, we can just look right at that and know that that's true. Okay. All right, let's have a look at part B for this one. So if I want to find the average acceleration between 5 and 15 seconds, do I have a formula that solves for acceleration? Okay, so my formula for acceleration is VF minus VI over T. Okay, my final velocity happens at time 15 seconds, and it's positive 8 meters per second. Okay, and I'm going to subtract my initial velocity, which was negative 8. So my change in velocity is 16, positive 16 meters per second. And that happens over 10 seconds. Right? So when I do that, okay, I should get positive 1.6 meters per second squared. Okay, everybody follow what I did there? Okay, just plugging numbers into the formula. As long as I can read the graph, I can solve these things easily by just using the formulas on my formula sheet. Okay, how many people are done C? Okay, let's have a look quickly at C then as well. Okay, if I want to calculate average speed, I need total distance and total time. Okay, distance, vector or scalar? We don't sound terribly confident here. Vector or scalar? Scalar doesn't have direction, right? So what do I need to do with these negatives? Not consider them. Okay, 40 plus 20 is 60, plus another 60 is 120, right? So the average speed is going to be 40 plus 20 plus 20 plus 40, okay, which is 120. And that happens 120 meters, okay, over 20 seconds. Okay, well, 120 over 20 is 6 meters per second. Okay. All right. Move on to number 6. Give number 6 a try. Okay. This one's going to involve a bit more shape drawing. It's a bit more like number 4 was. Okay. And it's kind of hard to tell because there's no grid lines on here, so I'll give you a little bit of help. Actually. Okay, just so you know where those go when they go down to the x-axis. Okay, I would say that the shapes we would want to draw here, okay, we want to make as many rectangles as we can because they're easier. Okay, so my thoughts on this would be, obviously we would want to have this triangle, okay, and then we would want to have actually that rectangle, right? I got to find the total area underneath my line. That takes up a pretty significant chunk of it. Would you agree? That eliminates having to find a whole bunch of little rectangles. One big one is a lot easier. Okay, then I would say probably this triangle here, okay, this rectangle here, this triangle, okay, and this triangle. I'd say those are the shapes you need to find the areas of. Okay, remembering that when we find those areas, we're taking average velocity and multiplying it by time. Okay, that's really what we're doing when we calculate those areas.